Hello everyone, I'm Dr. Akanksha Gupta, Assistant Professor, United Institute of Pharmacy. Today I'm going to discuss about the chemistry of the phenol. It is a very important topic in pharmaceutical organic chemistry, subsequent PP301T. So here I'm going to discuss about the introduction, different reactions, resonance and activity of the phenol. So basically, phenol is an aromatic compound having one benzene ring which is directly attached to the OH. So molecular formula for the phenol is C6H5OH, and so basically here phenyl group C6H5 and it is connected to one OH, so it is called as phenol. All suffix is added to in IUPAC nomenclature when we have one hydroxy group. So it's a name given is as phenol. So it is a nomenclature of the phenol. So here we can see that in phenol, one benzene ring which is directly attached to the OH group. So it is a phenol. And when two hydroxy group is present in the adjacent position, we can call it C1 and C2. So we can give the name 1,2-dihydroxybenzene, or we can also call it orthohydroxyphenol, and the general name for this structure is the catechol. When OH group is present in 1 and 3 positions, then we can call it 1,3-dihydroxybenzene or metahydroxyphenol. And the general name for this structure is the resorcinol. So 1,2-dihydroxybenzene is known as catechol. 1,3-dihydroxybenzene is known as resorcinol, and 1,4-dihydroxybenzene, that is the para-hydroxyphenol, is known as hydroquinol. So it is the nomenclature of the phenol. And when we have some other functional group, so here we can see that one another group is present, and the position is the 1 and 2. So we can call it 2-nitrophenol, and we can also give the name ortho. It is position 1 2, that is the ortho. So it is also known as orthonitrophenol. Here we can see that the position is basically 1 and 3. So we can call it 3-nitrophenol or metanitrophenol. And here the position is para, that is 1 4. So we can call it ortho para-nitrophenol or the 4-nitrophenol. Here we can see that the 3-nitro group is present at position 2, 4 and 6. So the name is 2,4,6 trinitrophenol, and in general name it is known as the picric acid. Now I'm going to discuss about the structure of the phenol. So basically, in phenol, I have already discussed that one benzene ring is directly connected to the one OH group. So here the alcohol functional group, that is the OH, consists of one oxygen atom bonded to sp2 hybridized aromatic carbon atom and hydrogen atom via sigma bond. Both carbon oxygen and oxygen hydrogen bonds are polar in nature, and here the conjugation exists between an unshared electron pair of the oxygen and the benzene ring. So this results in, as compared to alcohol, that is a shorter carbon and oxygen bond, a more basic OH group, and a more acidic OH proton. Now, coming to the physical properties of the phenol, phenol is basically the colorless, crystalline, poisonous solid with phenolic odor. And melting point is 41 degrees centigrade, and boiling point is 182 degrees centigrade. It is basically sparingly soluble in water, forming pink solution at room temperature. It is completely soluble above 68.5 degrees centigrade. Here we can see that at room temperature it is sparingly soluble in water, but above 68.5 degrees centigrade it is completely soluble in water. It can cause blisters on the skin, and it is used as a disinfectant, and it is used in the cleaning of the washrooms. Phenol is basically acidic in nature. It is a very weak acid. So here the reason for its acidity, here we can see that phenol is present in the different resonating forms. Here we can see that in first structure Basically, these are the lone pair electrons on the oxygen atom. So these lone pair of electron, one of the lone pair of electron move towards and participate in the conjugation of the benzene ring, resonance of the benzene ring. So here we can see that this electron pair comes uh, to this carbon atom. So electron density at this carbon atom increases, and that is why this double bond breaks. And here we can see that here is no double bond. So when this bond breaks, the electron density increases at this carbon atom, and here then the bonding between these second and third carbon atoms starts. So here we can see the double bond is here. So likewise, this double bond break, and the electron density comes to the fourth carbon atom. So overall, where we can see at last the electron pair comes to the this position, and finally it goes to the oxygen of the hydroxy group. So here again we can see in the last structure that though both electron pair comes to that original position. So here we can see that phenol is basically present in the resonating in these in resonating forms. And the reason behind the acidity of the phenol, here we can see that oxygen atom, in the previous structure, we can see that oxygen atoms have one plus charge. That is that denotes the electron deficiency on the oxygen atom. Just because one electron pair participate in the resonance, so at that point the electron density decreases on the oxygen atom, so it is slightly electron deficient. So we put the positive charge to just to represent the low electron density or electron deficient condition. So when oxygen have less electron density, it is the octet is incomplete. So to complete its octet, basically oxygen atom attracts, withdraw its electron pair of the hydrogen atom. So in the next here we can see that this OH bond breaks, and the sharing electrons of this O and H oxygen withdraw these electrons. So here we can see this bond breaks, and hydrogen, that is a proton releases. And we know, as we know that if the proton releases easily, so the atom, this compound will be the acidic in nature. So it is the reason behind the acidity of the phenol. So here it is a comparison of the acidity of the phenol and carboxylic acid. So basically, as we know that carboxylic acid is also present in the resonating structures. So here, these are the structures, resonating forms of the carboxylic acid. So here we can also see that the H atom releases very easily. That is why it is the acidic in nature. And the electron, these are both these are the resonating structures of the carboxylate ion, and these are the hmm, less stable. These are not equivalent, hence less stable. So resonating structure of RCO minus, that is the carboxylate ion, are equivalent and hence more stable. The RCOH have tendency to undergo ionization and form more stable carboxylate ion and proton. So, and here the different resonating structures of the phenoxide ion are not equivalent. Here we can see here that these are different structures. So the resonating structure of carboxylate ion are equivalent. Hence, carboxylate ion is relatively more resonance stabilized than phenoxide ion. Thus, the carboxylic acid is more acidic than phenol. So, as we know already, that phenol is less acidic in nature. So, because of these unstable structures. So this is the acidity order of the different compounds. Here we can see that carboxylic acid is the more acidic as compared to the carbonic acid, then phenol, then water, and the aliphatic alcohol. Now, coming to the effect of substituent on the acidity of the phenol. So we have already seen the resonating structure of the phenol. So here we can basically there are two types of substituent, that is the electron attracting and electron donating. So when we put electron attracting or withdrawing substituent, so these tend to disperse the negative charge of the phenoxide ion, thus stabilize the ion present of the oxygen atom, and so they increase the acidity of the phenol. Here we can see that electron, if we put the electron donating substituent, these basically tend to intensify the charge, destabilize the ion, so diminish the resonance and decrease the acidity. So basically, when we put the electron withdrawing group, the acidity of the phenol increases, and if we put the electron donating group, then acidity of the phenol decreases. Now coming to the different preparations or synthetic methods of the phenol. So phenol can be synthesized by the benzene sulfonic acid. Here we can see that it is the benzene sulfonic acid. So sodium benzene sulfonate is here, and when we react it with 10% aqueous NaOH, so here we can see that this intermediate forms, and finally this is basically sodium phenoxide. And basically here we can see that so this ONA reacts with HCl, and then NaCl byproduct forms, and this OH comes with this oxygen, that is the phenol. So finally we get the phenol, which is our final product. The next preparation method is the Dawes process. In the Dawes process, we can see that basically we can use the halobenzene. So here we have taken the chlorobenzene, and when chlorobenzene is react with 10% NaOH at 360 degrees centigrade, so here we can see that this H and this Cl, that is the HCl. So HCl removes, and ONA gets attached to the benzene ring. That is again the sodium phenoxide, and that HCl, which has already formed in the reaction medium, that HCl reacts to this sodium phenoxide. Then we get the NaCl byproduct and this phenol in our as our final product. In the next method of the phenol, we can get the phenol structure by the oxidation of the cumene. So it is the structure of the cumene, and when we react with oxygen, then we form this intermediate product. It is oxidized product of the cumene, and then we react it with the H2SO4. So here we can see that finally we get the phenol as a final product. In the next method, we can get phenol by the aryl diazonium salts. So here we can see that it is the aniline, and when we react aniline, that is the aromatic amine, with the nitrous acid at 0 to 5 degrees centigrade in the presence of NaNO2 plus HCl, that is. So then here we get the diazonium salt, benzene diazonium basically. So when we react benzene diazonium, and when we hydrolyze it in the presence of acid, so we will get the phenol as our final product. Now, it is a different activity, different reactions of the phenol. Basically, phenol gives electromeric substitution reaction. So this is the basically reaction of the benzene ring. So, as we know that OH is present in the benzene ring, that is why the next substituent comes according to the direction of provided by the OH. So, OH is basically ortho-para directing group. So, here we can see that electrophilic substituent which comes for the reaction, it attracts at the ortho and para position. So, basically in the electrophilic substitution reaction of phenol, we get the ortho-meta substituents derivatives. This is the different conditions for the reactions of the benzene and the phenol. So for nitration of benzene, we use concentrate nitric acid in the presence of H2SO4, but in case of phenol, we just need the dilute nitric acid. And in sulfonation, again, sulfonation of benzene, we use dilute H2SO4, but in case of phenol, we need concentrate H2SO4. In halogenation of benzene, basically we use iron and halogen, but in case of phenol, we just use the halogen. In alkylation reaction of benzene, basically we use any haloalkane, and with the Lewis acid. With Lewis acid for alkylation of benzene, Lewis acid is important. So here we use the aluminum anhydrous aluminum chloride. And in case of phenol, we can use with RCl and AlCl3 also, but we can do alkylation with the help of ROH or H plus in acetic medium, basically. Then in acylation reaction, so basically in benzene, for alkylation of benzene, we use again any Lewis acid, that is the anhydrous aluminum chloride, and we react with it with RCOCl, that is the acyl chloride. And in case of phenol, again it is the same reagent. For nitrosation, benzene didn't give any product in the nitrosation, but phenol gets nitroso compound. Nitroso compound after the nitrosation with NaNO2 plus H plus, and nitrosation, basically NO group is added to the phenol, and it comes into the para position of the phenol. And if we talk about the oxidation of phenol, so phenols are very reactive towards the oxidizing agent. The oxidation takes place through several steps, eventually destroying the ring. So basically, the ring get destroyed, and the basic nature of the phenol is will change. When we come to the some specific reaction of phenol, so first one is the Kolbe-Schmitt reaction. So it is the basically carboxylation reaction. So here we can see that we react the sodium phenoxide with CO2 at 15 degrees centigrade. We get the ortho sodium carboxylate product, and at 240 degrees centigrade we get the para substituent of this Kolbe condensation reaction. Here, I'm going to discuss about some difference between the alcohol and the phenol. So, as we know that both are having one hydroxy group, but in case of phenol, the OH group is directly attached to the alkyl group, and in case of phenol, OH group is attached to an aryl ring. And when we talk about the alcohol, so it is basically the hydroxy derivative of alkane, and in case of phenol, it is the hydroxyl derivative of benzene. And the general formula for alcohol is ROH. We can represent it with ROH, but general formula for phenol is H5OH. And basically, when we talk about the alcohol, then alcohols are the colorless liquid. And when we talk about the phenol, then phenol is colorless crystalline solid, basically. The characteristic smell of alcohol is quite sweet and some having burning taste, but phenol is having a characteristic odor. Alcohol is readily soluble in water, and solubility decreases in higher alcohol. And in case of phenol, I have already discussed that it is sparingly soluble in water at room temperature, and it is completely soluble in water above 68.5 degrees centigrade. So it is all about the phenol and the chemistry of the phenol. So thank you, everyone.